Okay, so this is our formula for how couplings change under RG flow if that flow is close to the free field fixed point. And we've already applied that formula to the case of a term that looks like m squared, phi squared in the action. And we found that m prime squared is bigger than m squared. This tells us that the mass grows under the RG flow if we're close to the free field fixed point. A term like this that grows, we describe that by saying you have a relevant operator. So phi squared is a relevant operator in D is equal to 4. Now I want to consider another example. So consider a term like this in the action. It's an integral d4x lambda 6, that's the name of the coupling, phi to the power of 6. And again, using the boxed equation at the top, lambda prime 6 will be equal to, we've got 1 minus b, it's to the minus d, so this is minus 4, plus m. M is the number of derivatives, there's no derivatives, plus n over 2, that's 6 over 2 is 3 fields, times by d minus 2 is 2. And this is lambda 6. Minus 4 plus 6 is 2, so we've got 1 minus b squared, lambda 6. Remember, 1 minus b is less than 1, and that means that lambda 6 prime is less than lambda 6, and that means under RG flow close to the free field fixed point, lambda to the 6 decays. It gets smaller, okay? So it starts to decay. There's some language for this. We say that phi to the 6 is an irrelevant operator in D is equal to 4. So I'm always being careful to say in what dimension I'm in, because whether an operator is marginal, relevant, or irrelevant depends on what dimension you're in. Now, one final example, if we've got an integral d4x lambda phi to the 4, you can plug the numbers into the formula. You will find that lambda prime is equal to lambda. So that means that this coupling, so under RG flow, again, close to the free field fixed point, lambda neither grows or decays. The language that we use for this, we say that phi to the 4 is and now we use the language of marginal. So it is a marginal operator. In D is equal to 4. Good. So we can classify all terms in the action as either relevant if they grow during the RG flow, irrelevant if they decay during the RG flow, or marginal if they neither grow nor decay. Now, I want to remind you of the physical picture that you should have in mind, okay? So what we've got is we've got some enormous energy scale lambda. And then sitting at the bottom here, this is where particle physics happens, okay? At this very low energy at the bottom here. And this transition from this enormous energy to this very low energy, this is what the RG flow does. So you'll use the renormalization group flow to flow down to particle physics energies. Concretely, you'll do steps 1, 2, and 3, and then keep repeating until you're all the way down to low energies. So during this RG flow, you'll find that all irrelevant operators are set to 0. All irrelevant operators are set to 0. So by the time you get to low energy, all irrelevant operators have disappeared. So only marginal and relevant operators appear in the low energy action. Okay, so this is very interesting. We have removed all irrelevant operators. And now I'd like to discuss the interpretation of that, because there is a nice interpretation of that, and we'll be able to make contact with the earlier ideas of Feynman, Schwing, and Tomonaga, or the earlier description. So really, Wilson is the correct way to think. And what Wilson has proved to you is that as long as you're close to the free field fixed point, you know, so as long as you're dealing with weak coupling and perturbation theory, you know that all irrelevant operators are set to 0. It's only the marginal relevant operators that appear in the low energy action. Now, I want to start with just a little bit of dimensional analysis. So you know that we've set h bar is equal to 1. You also know that the action, which has the dimensions of h bar in our units, is dimensionless. Okay. What I'd like to do is consider lambda mn integral dx d phi n term in the action. So I want to study this term, and I'm interested in knowing what is the dimension of that coupling lambda mn. Well, to work that out, I'll take the dimension of lambda mn, then I'll have length to the d. That's the dimension of the measure. I will have length to the minus m, because each derivative comes with an inverse length. And then we've worked it out a few times. I think that you'll be able to do this, but the dimensions of the field phi is L to the, what is it? It is 2 minus d over 2. So that's the dimension of the field phi. And we've got n phi's here, so we will have L to the n times 2 minus d over 2. And then this is a term in the action, so this must be L to the naught. So this equation tells us that what the dimension of lambda mn is. So let's call this L to the p. And what is p? P will be equal to minus d plus m plus n into d minus 2 over 2. So that's the dimension of the coupling. Lambda mn is L to the p, and p is equal to minus d plus m plus n times by d minus 2 over 2. Now, I want to remind you of the formula that we derived for how the couplings flow. So let's just capture this formula and take it downstairs. So duplicate, good. Okay, so look at this. Okay, if you take a look at this formula, lambda prime is 1 minus b to the power of minus d plus m plus n d minus 2 over 2, but that's just p. So we see, in fact, that this transformation law is dictated by dimensional analysis. And what's more, we said that whenever 1 minus p appears with a positive power, that's when we have an irrelevant operator. So whenever the power of 1 minus b is positive, we have an irrelevant operator. So for an irrelevant operator, so irrelevant operator, now we see what it means. It means that p has to be greater than 0. So this means that any coupling with a positive length dimension corresponds to an irrelevant operator. Now I want you to remember what we proved with power counting. With power counting, we proved that if you have a coupling with a positive length dimension, this leads to a non-renormalizable quantum field theory. So remember, when we studied Newton's gravitational coupling, this was L squared, and we immediately said this was non-renormalizable. So in actual fact, there's an incredible translation between the two. The irrelevant operators are what Feynman, Schwinger, and Tominaga would have called non-renormalizable interactions. The marginal and relevant operators are what Feynman, Schwinger, and Tominaga would have said correspond to renormalizable interactions. Well, Wilson has explained to you why, when you do this RG flow, all of the irrelevant operators are set to 0. So he's explained to you why only marginal and relevant operators appear in the low energy actions. So he's actually proved that particle physics should be described by a renormalizable quantum field theory. At low energies, you just have a marginal and relevant set of terms in your action. So your complete space of low energy actions is your space of renormalizable quantum field theories. Okay, so now let's just try to summarize a little bit. Let's just put down a few ideas. So what we've got is we've got the Feynman, Schwinger, Tominaga, Dyson, or old version of QFT. And I want to contrast this a little bit with Wilson's modern or new way of viewing quantum field theory. And let's just talk about the two of them. So there's a cutoff, lambda, in the Feynman, Schwinger, Tominaga, Dyson view. This cutoff is a regulator. It's not something that's physical. It's introduced to define infinite quantities. So it's a mathematical device. There's nothing physical about it. You do your renormalization procedure, but you want to take lambda to infinity at the end of the day. It doesn't have a meaning. For Wilson, lambda is a physical scale, and every quantum field theory comes with a physical scale. Feynman, Schwinger, and Tominaga would tell you that quantum field theory is fundamental. It is a complete theory of nature. It's a fundamental interaction. What Wilson will tell you is that quantum field theory is effective. It only holds on length scales which are larger than h bar divided by lambda. If you want to go below h bar over lambda, to lengths which are smaller than h bar over lambda, you'll need to add new physics. So quantum field theory is not a complete description. It's not a fundamental description. It's an effective description. And new physics will appear at length scales below h bar over lambda. What could this cutoff be in the quantum field theory of particle physics? Well, maybe it's the grand unification scale. Maybe it's the quantum gravity scale. It's some scale below which new physics will become apparent. Feynman, Schwinger, and Tominaga organize the theory by loops. So they do a loop expansion. When you calculate loop diagrams, infinities appear very suddenly as you're calculating a loop, and they're meant to be small because they come with powers of h bar. So the loop expansion is also an h bar expansion. So it's a small parameter. You're assuming that you've got weak coupling. Wilson doesn't organize things according to loops. He organizes things according to momentum shells. So he's broken momentum space up into shells, and you start off by integrating out the shell of the highest modes. Once you've done that, you go to the next shell, and so on. So you've organized the theory according to scale. The highest momentum modes correspond to very short distances, and you slowly keep integrating out the higher momentum modes until you eventually get a theory that's defined on long length scales, an effective theory defined on large length scales. So completely different way of viewing it compared to Feynman, Schwing, and Tominaga. In the Feynman, Schwing, and Tominaga picture, infinities appear, and you need to use this idea of renormalization that appears, well, suspect. There's many things you could complain about in the theory of renormalization. In Wilson's way of viewing them, there are no infinities, okay? Quantities just don't diverge, no divergences. You organize the theory, or you classify the different terms inside the theory as either relevant, marginal, or irrelevant. Feynman, Schwing, and Tominaga tell you that you must use a renormalizable QFT, and this must be used so that you can actually carry out the renormalization program. Otherwise, you can't even renormalize your theory. There will be infinities that you can't define. From Wilson's point of view, you don't declare that you need renormalizable quantum field theories. You explain that low energy physics is described by a renormalizable QFT because it's a QFT that only has renormalizable QFT. And the reason why it's renormalizable is it only has marginal and relevant terms. Okay, so that's just a bit of a comparison between the two. And I hope you can see what Wilson achieved. What he achieved was quite remarkable. He actually understood what quantum field theory was, that it should be organized according to scales, that there are relevant, irrelevant, and marginal operators, and that at low energies, of course, you're going to get a renormalizable quantum field theory. That's what the low energy theory has to look like. Good.